Okay, welcome back. Happy Tuesday. Today is March the 7th. We're going to cover lesson 13 in its entirety, and we are going to start lesson 14. I want to point to something a little bit unusual coming up on our calendar. So we've got our first test. We've got our first test coming up on March 14th. That is 1 week from today. And in fact, it's a very special day, not just because we have our first test, but for mathematicians, why is March 14th special? It is Pi Day. What a wonderful way to celebrate Pi Day with our very first test. So that's coming up a week from today. Okay, but to be clear, even though next class we're doing lessons 14 and 15, if you take a look at this row right here, material covered on the first test is lessons 1 through 13. The test that we are taking is only up through 13. So once we finish 13 today, that's the end of the new material for the test. And then we're going to move on to 14, which is not on the test. And next class, we're doing 15, not on the test. And it's a little bit strange for us to do lots of stuff that's not on the test. The alternative would be to take our test on Thursday coming up, 2 days from now. And I just felt like that wasn't super fair to have us covering material that's on the test and then have you take the test 2 days from now. So the test is a week from now. We're going to be doing some stuff that isn't on the test between now and then. But lesson 13, the first thing we do today is. Any questions on the calendar? Okay, so here we are on page 105. No, we're finishing up the old packet right now. We'll talk about the new packet later during the period. Okay, our daily summary, page 105. In this lesson, we continue to look at applications of systems of linear equations. These applications involve mixtures using percentages and travel. I mentioned last time, these applications are a bit tougher than the ones in our last lesson. Number 1, antifreeze is a mixture of the chemical glycol and water. So if you go to the auto supply store and you pick up a container of antifreeze, a bunch of it is water and a little bit of is this chemical called glycol. An auto mechanic keeps bottles of antifreeze in 2 strengths. The first bottle is 20% glycol and the rest is water. Remember, it's just a mixture of water and glycol. And the second bottle is 35% glycol, the chemical, and the rest is water, okay? So we got 2 different strengths. The 35% is more chemical than the 20% one. You understand what these different jugs mean? Is it clear? 20% is this chemical and the rest is water. 35% is the chemical and the rest is water. Would you guys agree that I could mix these 2 jugs, the 20% and the 35%, and make a new mixture that is some percentage between 20 and 35? Like you could use all the 20 and then it's just 20, or you could use all the 35 and then it's 35. If I went like equal amounts of both, what percentage would I end up with? It's 27.5, right in the middle, right? Like if I just do equal amounts of both the 20 and 35, then the percentage of the mixture will be right smack dab in the middle. But if you use a little bit more 20 and a little bit less 35, the percentage kind of creeps towards the 20, right? Or you could use more 35 and get the percentage to be really close to 35. So we can make any percentage we want between 20 and 35. Here's what this mechanic wants to do. The mechanic needs to create 12 quarts of antifreeze that is 25% glycol. 25% is the strength that we are after for this mechanic, okay? Are we going to use more 20 or more 35 to build the 25? We got to use more 20 because the 25 is closer to the 20 than the 35. But we want to know exactly how much to use. So that's our question. How much of each bottle should be in the mixture? So we'll define our variables. Again, the question often tells you exactly what the variables should be. How much of each bottle? Okay, those are the variables. We'll let L equal the amount of antifreeze in quarts in the 20% concentration, and H is the amount of antifreeze in the 35% concentration. Low and high is what those letters stand for. Okay, let's start filling in. The amount of antifreeze in quarts for the 20%, that's what we called L. The amount of 35%, that is H. Remember, the word antifreeze means both the water and the chemical glycol. It's the 2 of them together. How many quarts in the final mixture? No, that's the percentage, but the number of quarts of liquid is 12. That's what we're trying to build. And just from that first column, maybe you can already read off one of our equations. L plus H equals 12, right? That's one of them. Okay, the percentages are easy to fill in. The percent of glycol in this top row is 20. So what number am I putting here? 0.20, right? Make sure you convert your percentages to decimals. Next one, 35% becomes 0.35. In all of the tables we did last class, this bottom middle was left blank. But here it's a number. The final mixture is supposed to be what percentage? 25. So we put 0.25 right there. Okay? Okay, one more time. Antifreeze is a collection of water and the chemical. We're only interested in how much of the chemical we have, the amount of glycol, the amount of chemical, okay? And so if, for example, I told you that I had like, I don't know, 50 quarts, you don't need to write this, of the 20% solution, what would you do to these two numbers to find out how many quarts of those 50 are actually the chemical glycol? What's that? We'd multiply, right? 50 quarts times 20%, 50 times 0.2, right? It's 10. 10 of these quarts, that's 20%, 10 of these quarts are the chemical glycol, and the other 40 of those quarts are just water, okay? What I'm interested in is how do we get the amount of glycol? In this case, it's just 50 times 20%. In this first row, it is 20%, but I don't know it's 50. It's L is the number of quarts of liquid. So it is just L times 20%. So we'll put that right here, 0.20 L. And lo and behold, again, how do we build this last column? We multiply the first two columns. Next row, 0.35 H. Last row. I like the 0.25. 0.25 times 12. Isn't that how we built the last column? Just multiply the first two. And this is a first for us. Typically, this bottom number here is given, just up in the problem someplace. But here, we have to calculate it. We know we're trying to build a 12-quart solution, and it's got to be 25% glycol. So we're just doing 25% of 12, which is 3, right? Just a quarter of 12. Okay, so let's get our equations here. This guy, what's the equation for that one? L plus H equals 12, just go straight down. That's written right there. And then this guy, 0.20 L plus 0.35 H equals 3. That's there. And once you got your two equations, you solve using either substitution or the elimination method. We're not going to do that here right now. Questions on the setup? Okay, so let's take a look at the one last kind of problem we might have to tackle. All right, similar approach, like that same idea with the table up there, can be used for problems involving distance and rate and time. Let's just make up a quick example. Suppose that you drive 5 hours at 40 miles per hour. How far did you drive? Drive 5 hours at 40 miles per hour. How far did we go? 200 miles, right? We just do the 5 times 40, right? Okay, so what that means is that if you take the time, that's the 5 hours, and you multiply it by the rate, that's the speed, what word do we get? Distance, right? That's the distance traveled. Okay, your speed multiplied by your time is your distance traveled. And so that's just written right up here in words and then again in symbols. Okay, so it's an equation that you all know. Even if you don't know it in symbols, it's something very intuitive to us. So we're going to use that equation in this next kind of problem. Irma flies her plane with the wind and makes a 450-mile trip to Saratoga, New York in 3 hours. The return trip against the wind takes 5 hours. We want to find the speed of the wind and the speed of the plane in still air. So it's the same trip we're making, once to Saratoga and once coming back. But going out, we have the wind helping us, and coming back, we have the wind going against us. And so do you guys buy that it might take a different amount of time? Even though it's the same distance that we are traveling, it might take a different amount of time because you can go faster with the wind and you go slower against the wind. Okay, so the question here again is given. It says, find the speed of the wind and find the speed of the plane in still air. Those are our variables. W is the speed of the wind in miles per hour. P is the speed of the plane in still air in miles per hour. Okay, let's start filling in our table. First, the time. Trip to Saratoga with the wind. How long did that take? 3 hours, right? And then the return trip against the wind took 5. Okay, so here's the trickiest part. We got to figure out what our actual rate of speed is. Now, the speed of the plane we called P, but you can't just put P right there because you are getting helped by the wind in the one direction and then you're getting hurt by the wind in the other direction. So it's not just P. Let's just make up a quick example here. Suppose that P is 80 miles an hour. This is how fast our little plane would normally go without the wind affecting us. And suppose that the wind speed is 10 miles per hour. Just assume it's constantly 10. If the wind is helping us, how fast are we actually going? 90, isn't it? Right, 80 miles an hour on our own, plus a 10 mile per hour boost from the wind. So we just add those and we get 90 miles as our true speed. If we're going into the wind, so the wind is coming this way and we're flying this way, then how fast are we going? It's only 70, right? Because normally we'd be going 80 on our own, but the wind is hurting us by 10 miles an hour here. So we don't get to go 80, we go 70 because we're fighting the wind. Does that make sense? So then in general, if you want to know how fast you're going with the wind, you just take your two speeds and you add them together. P plus W is what goes in there. And if you are going against the wind, we just subtract the speed of the plane minus the speed of the wind. Okay, so here's the fact. Every time you do one of these kind of wind problems, the speed with the wind is always P plus W and the speed against the wind is always P minus W. I could change the context. I can make it a boat. What kind of like thing helps or hurts a boat's speed? The current, right? Like imagine you're in a river and you're going with the current, so you go faster than normal, against the current, slower than normal. It's just the same. Add the two speeds, subtract the two speeds. But there are a couple of ways to go wrong on this one. First of all, if you're not careful, you could say, okay, I just have to add the two speeds here. Don't write this. And I have to subtract the two speeds here, right? One of them is right, but one of them is wrong. Which one's still okay? Top one, W plus P is the same as P plus W. But the bottom one is not right. What would the bottom one be as a number if we did W minus P in this case? Negative 70, right? We'd be flying negative 70 miles an hour. And the algebra will still do stuff and you'll get a ridiculous answer at the end because you're trying to travel at negative 70 miles an hour. So you got to make sure you know more than just, oh, I add them and I subtract them. It's always the speed of the plane first or the speed of the boat first and then subtract the wind or subtract the current. Other common mistake is to not be so careful about where you put these times. Put 5 there and 3 there. What's the problem? Yeah, somehow we're setting it up so that it takes longer when the wind is helping us. And again, that's going to lead to very bad answers. So just be really careful that you put the times in the right rows. Okay, the last column, let's fill in. We're going to do exactly the same technique that we've done over and over again. We know that the rate times the time is distance. We are after the distance, so we're just going to do the rate times the time. I'll put the 3 first, times P plus W. Those parentheses are mandatory. And then the last spot, what's in the last spot? 5 times P minus W. That's good there. Right? So that's, again, the last column is the product of the first two. Okay, now we need some equations. There's only one piece of info we haven't used yet. This is the 450. We know that 450 is the distance between the start and Saratoga. So that means this thing must equal 450, agree? What about the other distance? It's also 450. It's the same trip, right? You're going out and then you're coming back. 450 miles both times. I also want to point out there is no third row here. We don't have a total. There's nothing given in this bottom row. Every other probably did had a total or a mixture kind of row, not this one. Okay, so those are our two equations there. You can solve them later on if you want. The answer is given. Any questions on that? Okay, so activities start on the next page. Nope, 2 pages away. First of all, you're going to have to make your own table. So feel free to reference the tables that we just made here today. Second of all, we're going to do just like we did last class. You're going to set up and just get to the place where you've written 2 equations down, but then don't solve them. Move on to the next one, write 2 equations, move on to the next one, okay? Only after you've got all of the equations written down do I want you to go back and start solving with substitution or elimination.